Okay, in this video we want to talk about the second degree approximation with what are called Taylor polynomials. So we talked previously about how to do a linear approximation, which is really just the first two terms here. If we're centered around a point A, so it would be f of A, so at that point at least they agree. And of course their derivatives at that point would agree. So for a quadratic, we just say, well, we want to add on another term, x minus a squared. We want it to be second degree with some constant. Now, following the reasoning before, we definitely would prefer our approximation to definitely agree at that point. We'd also like our approximation to agree as far as the derivative. And taking it further, there's other ways we could decide this, but we decide here for the quadratic, we'd like the quadratic to agree on the second derivative as well. So it kind of at least has the same orientation or concavity as the graph has around that point. So if we try to evaluate P2 at A, we would have A minus A, which would cross out this term. A minus A squared would cross out this term. So of course, P2 of A does agree with f of A. And if we take the derivative, P2 of A, well, the f of A term would go away. We'd have f prime of A times 1, which is be f prime of A, plus the derivative of this part, which would be 2c2 of x minus A, but we're evaluating it A, so that term would cross out as well. And so P2 of A is just equal to the derivative. So it agrees on the first derivative. If we take the second derivative of this formula, we'd have P2 of A equals T times C2, and we want that to be equal to the second derivative, so that means that C2 must be the second derivative divided by 2. So our formula for the quadratic approximation then is our linear approximation with the additional term f double prime of A divided by 2 times x minus A squared. And then that gives us a quadratic approximation. We're going to see here a little bit later how the quadratic approximation looks. So armed now with our linear and quadratic approximation, we now ask this question. We want to find the linear and quadratic approximations for the function square root of x around x equals 1. Then we're going to use those two approximations to compute or approximate square root of 1.1, which to 5 decimal places is 1.04881. Okay, so we want to compute the first degree linear approximation, straight line approximation, and then we want to compute the quadratic approximation for the square root of x function with its center around x equals 1. So we continue here by saying, of course, our function is square root of x. So to do the linear approximation, we need to know what f prime is. And to do the quadratic approximation, we're going to need to do f double prime. So f prime, derivative of square root of x, where that's x to the 1/2. So that would be 1/2 x to the negative 1/2, or 1 over 2 square root of x. And then the derivative of that, the second derivative, would be negative 1/4 times x to the negative 3/2. Now at this point I stopped. I didn't go ahead and rewrite that, bring the 3/2 down, because now what I want to do is evaluate each one of these things at my pivot point here, at my center point for this approximation. So f of 1, of course, would be square root of 1, which is just 1. F prime of 1 would just be 1 over 2 square root of 1, which would be just 1/2. And f double prime, well, x to the negative 3/2 evaluated at 1, that would just be 1 to the negative 3/2, but 1 to anything is just 1. So f double prime of 1 would just be negative 1/4. And so now at this point we can write out our approximations. Okay, so we're going to begin first with the linear approximation. So P1 of x is going to be f of 1 plus f prime of 1 times x minus 1. Okay, and so we just plug in here our coefficients, f of 1 and f prime of 1. So we get P1 of x is equal to 1/2 times x minus 1. So that's the linear approximation. And there's no need for us to go distributing through and simplifying. This is perfectly fine, kind of standard way of writing it out. So remember the second degree approximation. Well, actually, hold on. Let's compute it. First, P1 of 1.1 is 1.05. Is 1.05. And so you can see at least two decimal places. This is a fairly decent approximation for 1.1. It's pretty close to 1. So our approximation is actually pretty accurate here. And then we move on to P2. P2 is going to look just like P1, except it's going to have the additional term, f double prime of 1 divided by 2, where that's what our result from the last page said, times x minus 1 squared. So we're just going to plug in our number, which would be negative 1/4, divided by 2, make that negative 1/8. So that we get P2 of x is 1 plus 1/2 times x minus 1 minus 1/8 times x minus 1 squared. So notice here how P1 is actually an over approximation. It's bigger. So P2 is actually taking off the next term. So it's actually going to get smaller. It's going to give us a value that's at least smaller than the 1.05 answer. So when you plug that 1.1 in, you'll get P2 is equal to 1.04875. So we're actually accurate here if we round it to 4 decimal places. Now a little later we're going to talk about P3, what P3 looks like and how it relates to this thing. But the last thing I want to show you here is a graph of square root of x and my two approximations, my straight line approximation and my second degree or quadratic approximation. So here's the graph. The green graph here is my square root function. The black line here is the tangent line approximation, first degree approximation. And then this blue graph is the square root approximation. And you can see as you look at the graph here that the blue graph remains closer to the green for a little bit longer. But eventually, of course, it differs as well because it is an approximation. We're approximating the square root graph with a quadratic. And so it is, of course, off, but it definitely appears a fair bit closer. So this is the second degree or quadratic approximation, or what we call a second degree Talyor polynomial.